introduce what Newman projections are. So Newman projections are a way of visualizing molecules, okay? And they allow us to visualize the stability of the molecule associated and as it changes when we rotate around one of the sigma bonds. So, before we jump into this, let's zoom in over here to what I've drawn. So I actually, well, let me zoom out real quick. So here we've got 1, 2, 3, 4 molecules. Well, they're all the same molecule. It's just at different stages of rotation. So this molecule has a 1, 2, and then there's a carbon back here that we can't see. So it has 3 carbons. So let me show you what this molecule looks like. It is propane, and it looks just like this, okay? Now what we're going to do is we've got carbon 1, carbon 2, and carbon 3, but we're going to look down the carbon 2 to carbon 3 bond. We're going to look down the barrel of the bond, and because we're looking down the barrel of that bond, we can't really see the bond because we're only able to see, you know, the top point of it, if you will, okay? So when we look at it from the side, we can clearly see, ah, yes, there's a bond here. But if I look down the barrel of the bond, you can't see it with that same angle. But that's what we're going to do, and that's what we do in Newman projections. Now we have this circle here in Newman projections, and a lot of people like to teach that circle represents the front carbon, or sometimes people say it's the back carbon. I don't like that. I mean, that's fine. You can do that. It'll still get you the right answer if you go with that. But the way I like to visualize it is I pretend that circle is actually a disc. So here I have drawn a disc. Now if I take a disc and I sort of poke a hole in the center of it and I just sort of run my molecule through the center of that disc, and I'm going to put it somewhere in the middle between carbon 2 and 3, okay? So my bond poked through the center of that disc, okay? Now, what we need to remember is that the front carbon, I can see the front carbon because it's in front of the disc, but I can't see the back carbon because it's behind the disc. Okay, and I can't see past that. Now the other thing is, bonded to carbon 2, we have invisible hydrogens. So let's just draw those in. So there's one, and there's another one. And to the back carbon, there's actually 3 invisible hydrogens. Okay. Now, if our point of vision, what color should I use? For my point of vision here, the disc is blocking some of my vision on that back carbon. Okay? So what happens is I can't see the back carbon, okay? That is behind the disc. So let's color that darkly. And I can't see the beginning of the bonds to the hydrogen because the disc is blocking those views, okay? But I can see the very last part of the bond and the hydrogen atom. You see how it's kind of peeking out? So the 3 bonds that are coming out of the back carbon, I can only kind of see the very tip of them because they're being obstructed by that disc. But for the front carbon, I can see the entire bond. I can see the entire bond. I guess we're using yellow highlighter. I can see the entire bond because they're all in front of the disc. Nothing's obstructing my view. And so when I look at these Newman projections, that's how I like to visualize it. I say, oh yes, this is the front carbon, and you can see that it's the front carbon because I can clearly see the entire bond from that carbon to its 3 different groups. But in the back here, this hydrogen is bonded to the back carbon, and so is this one, and so is this one. And how do I know that? Well, I know that because their part of their bond is being obstructed by my disk. Okay, so that's how it helps me to visualize what's going on here. All right, so what's the difference between these molecules? Well, I want you to notice that the front carbon actually stays the same. Oh, never mind, I lied. The back carbon stays the same. So you can see here, the back hydrogens are always at these positions. They do not move, okay? What moves is the front carbon, because here the front methyl group is going straight up, but here it has moved 60 degrees from its original position. Okay, we took the methyl group and we moved it down 60 degrees. Okay, so if I move it another 60 degrees, right, from this position down 60 degrees, now it's here. I can move it another 60 degrees, it'll be right here, and I can continue to do this all the way around. Okay. So what's important to notice is this energy diagram here. Okay, so this axis, the y-axis, represents potential energy, and the x-axis is as we are rotating in this case, we're rotating the front carbon. Although it doesn't matter, we could have rotated the back carbon and kept the front carbon still, we would have gotten the same thing, okay? Typically, when I'm working with Newman projections, I keep one of the carbons, either the back one or the front one, still, and I rotate the other one, okay? But notice the molecule's energy is very high when we have lots of crowding, lots of steric hindrance. Why do we have lots of steric hindrance? Well, because the groups on the front carbon and the groups on the back carbon are very close to each other. They're pretty much overlapping, okay? So that means that they're very close to each other relative to when we put them in a more staggered position. So if we take this methyl group and we rotate it 60 degrees down, here's where it ends up, okay? And so we're going to rotate around this sigma bond, and that's going to cause the front carbon groups to move, okay? So when the methyl group and hydrogens are slightly askew from the position of the back carbon groups, they have more room, essentially. They are not as close to each other, and so you don't have as much crowding, and therefore you don't have as much steric hindrance. And because you don't have so much steric hindrance, and which is caused by electron-electron repulsion, the molecule is in a more stable state. It exists at a lower energy, okay? But if we rotate that front carbon again 60 degrees, now they're back in a position where they're eclipsing each other, where they're overlapping. Suddenly the molecule again is at a high potential energy, okay? So as you rotate around a single bond, you can change the energy at which your molecule exists. And of course, because molecules want to be as stable as possible, they want to be in a low energy state. So it's preferable for molecules to be in a staggered, askew position than in an eclipsed position with a back carbon, okay? So let's go over a few terminology here. So eclipsed refers to when the front carbon and the back carbon groups are aligned on top of each other. So this is eclipsed, and anything where your bonds are, directly in front of or behind, that's an example of an eclipsed conformation. That makes sense. That's pretty much what an eclipse is. Staggered is when you have a 60-degree difference between the bonds and groups of the front carbon and the back carbon. So it's like when they're offset, okay, or askew. Okay. Okay. And so let's label these. Eclipse, staggered, eclipse, and staggered. Now, we're going to focus on a specific type of staggered. So there is something called gauche conformation, and there's another conformation called anti. Now, both of these, gauche conformation and anti-conformation, are a specific type of staggered conformation. So these are both types of staggered conformation. Okay, so what do we have here? So in the example that we used earlier, we only had one methyl group and everything else was hydrogens. Okay, but this example that we're going to give has a few different groups on the front and back carbons. So if you notice our front carbon, we have a phenyl group and a methyl group and a hydrogen, but the phenyl group is the largest, the methyl group is the middle size, and the hydrogen is the smallest. On our back carbon, which I'll use green for, we have an ethyl group, a methyl group, and a hydrogen. So the ethyl group is the largest and bulkiest, the methyl group is the middle, and then the hydrogen is the smallest, okay? So anti is the most stable staggered conformation. Okay, we know that staggered conformation is more stable than eclipse, but when you have multiple groups of different sizes, you can get differences in energy and stability depending on where your groups are relative to each other. So, anti is when the largest group on the front carbon and the largest group on the back carbon are completely as far away as possible. In other words, they're 180 degrees away from each other. So, for example, the largest group that I have on my front carbon is the phenyl, and the largest group I have on my back carbon is the ethyl. So what would they need to look like in order for them to be as far away from possible? Well, I'd have to rotate my phenyl group up to this position so that they would be 180 degrees or as far away from each other as possible. If I rotate my phenyl group up there, then that's going to subsequently rotate my hydrogen over one and this methyl group over one. So my resulting structure will look like this. So my pH will be there, hydrogen, CH3. Okay, and so the most important thing is that the largest group is 180 degrees away from each other. Now, if you can, and you have other groups on there, the best thing for you to do is have the biggest groups 180 degrees from each other, the medium-sized groups on the front and back carbon 180 degrees away from each other, and the smallest groups on the front and back carbon opposite from each other. So each of them lines up linearly to be opposite from their respective similar-sized version on the alternative carbon. Okay, so what do I mean? What I mean is here, these are the biggest, and they're 180 degrees from each other. Then we have the medium-sized groups, and they're 180 degrees from each other, or as far away from possible. And then we have our smallest groups on the front and back carbon, and they are also as far away from possible. So this is the most stable conformation of this entire molecule, and so we call it anti. We call it anti because this is when the large groups are completely opposite from each other. All right, but then you have gauche. Now gauche is kind of like the staggered version that's not anti, okay? So in this case, and if we were to rotate these again, so let's see, let me put my phenyl down here and my hydrogen here and my methyl group one more. So now I have this, okay? So both these conformations are not the most stable staggered conformations, but they're still staggered conformations. And to distinguish them from the most stable conformation, which is anti, we call them gauche, okay? So this is anti, and these both are gauche. Now in the next video, we'll do some practice problems with what we've learned here.